Hello, everyone. Welcome to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm host for today's webinar. Our guest speakers today are Andrew Legro and Nikita Mishra, who are with the Field Applications Engineering team at ABB. And before we get into their presentation, as we are in the habit of doing, we'd like to have the audience participate in responding to a couple poll questions. Clearly no obligation or liability, strictly to help our presenters understand people as they're coming to the presentation. So if you would please respond accordingly. I apologize in advance for any typos due to my fat fingers. So obviously the first question is to get a perspective on what your present job status is and what your perspective on the topic might be. We'll leave this open for another 10 seconds, give everybody a chance to participate. This is actually part 2 of a 2-part series that we started a little over a month ago, and we're aiming towards a discussion of digital switchgear, which is a foreign term to me. Okay, so it looks like we have a quorum on the participation. Here's how folks have weighed in. Excellent. And then the next question, how familiar are you with the ABB relay family? And again, this is not any precondition to receiving material. It's strictly just to get to understanding how much detail we need to get into the basics versus some of the more advanced concepts. So it looks like we have a quorum here. Here's how folks have responded. Excellent. And then finally, have you heard of the term digital switchgear? And I'd be a definite no on this one. So we will have an opportunity to answer questions at the end of the session, but feel free to use the question control box on the webinar palette to enter questions even during the presentation. We'll try to answer as many as we can. Here's how folks have responded here. Excellent. Again, thank you all for joining us today. And now I'd like to hand it over to Andrew Legro. Andrew, give me just a second and I'll hand you the podium. Okay, you can share your screen.
Okay, excellent. Good afternoon, morning to everybody. My name is Andrew Legro with ABB. I'm a field application engineer in Florida, USA. This presentation is a continuation, as Jim was saying, of something that we started a while back. Turned out there was just way too much information in the first part of it, so kind of extended it out to a second session. I'll do a little bit of review stuff with you, but the second half of this presentation will be on a related topic, digital switchgear, which is kind of application of relaying, and that'll be with Nikita Mishra. She's also a field application engineer, formerly with the relay division, so she's pretty knowledgeable about the product line. So she'll take over at about the 1:30 mark. So I will jump into part 2 of the protective relaying basics. Generally, the class was supposed to be a presentation to convey a really basic understanding of protective relays to engineers and technical people that may not be familiar with them, and maybe familiar more with low voltage equipment, low voltage breakers, specifically with the application and coordination element of protective systems and breakers and whatnot. So there are a significant amount of differences between relays, which are applied at medium and high voltage, versus low voltage protective equipment. They do basically the same function, but in a lot of ways in a completely different terminology, different methodology. So in part 1, we kind of covered what the protective relay is compared to a low voltage circuit breaker. We went over some concepts, and we based it on kind of the beginnings, which is the electromechanical relay. It's a really basic device, and we kind of built the terminology and technology concepts around that electromechanical relay due to its simplicity. And then we kind of branched off into the next generation of relays, which are electronic, numerical, multifunction devices. So that was part one. It extended a little bit. I did a little bit of part two in the first section, where the objective was to show some application and coordination examples of protective relays. So part two today will be focusing much more on the overcurrent protection and settings of relays. This is just going to be focused on overcurrent. No other bells and whistles and protective settings. We're not going to discuss those. There's way too much information. And then a little section on actually using the relays within EasyPower platform. And then, as I said, we'll jump over to a digital switchgear overview with Nikita, which is a nice transition, because the digital is sort of the cutting edge, state of the art stuff that we have in the medium voltage relaying and protection world. So part two, just a quick review between the protective relay, medium voltage, high voltage protection versus low voltage. The relay itself is only a piece of a larger system, whereas the low voltage breaker is a single package with everything built into it. So it's the brains plus the switch. It's all been pre-engineered. You really only have to call out that one device, the low voltage breaker, and it's a complete system. Relay is not like that. The relay is one piece of three primary components that you need. The protective relay itself, the current transformer, and then the circuit breaker. They can all be from different manufacturers. They can all be varying sizes and functions and types, technologies. The circuit breaker can be medium voltage or high voltage, air, vacuum, SF6, just a whole wide variety. So the point is, the onus is on the engineer to specify each component correctly and make sure that they work together as a system, and then understand what the dynamics of that system are, what the limitations, time delays, all that information. So a lot more engineering up front takes place in the protective relay / medium high voltage world than it does in the low voltage. Another weird item, this is a review from part one, is all the protective functions are named. There's a standard for each device type. So in this presentation, we're only going to focus on overcurrent, and so we're only concerned with these three device numbers. These are standardized by ANSI. 50, which is a non-delayed instantaneous overcurrent. 51, which is time delayed. And then the 52 device is the actual circuit breaker. So you'll see these designations come up. And then just real quick about the current transformer. This is just, I want to put this slide up basically to reinforce that the most important things that the relay protection engineer is concerned with the CT is the CT ratio, and then the accuracy class of it. And here's a quick table that I like this table because it shows essentially the standard ratios that are available. This is from ANSI C57, so this is these should be pretty readily available. So when you go in to apply your relay and breaker, these would be the selections you would have for standardized for CT ratios. Jumping into it, I wanted to break down the standard overcurrent for a relay. Consists of a couple different components, and I wanted to show them on the graphically on its time current curve. Hopefully a lot of you are familiar with the general concept of the time current curve, but in summary, it's a graph that represents when and under what conditions the circuit breaker or relay is going to operate, trip. essentially. And the x-axis is current, and the y-axis is time, and it's all increasing from 0, 0 at this point here at the origin. So going to the right on current is increasing current, going to up is increasing time, and then this blue line represents the line at which the relay will decide it needs to trip. So, for example, if you have a say it's 2 per unit current, and it's a fault or an overload, at 2 per unit current, the relay is going to remain closed until it hits this line, and this line is about 0.43 seconds. So essentially what this line is telling you is that at 2 per unit current, the relay will trip at around 4.3 seconds. Now, the curve's broken into a couple parts. The first device that we'll cover is the time overcurrent, which is a overcurrent that it's delayed and is proportional to the trip response is sort of inversely proportional to the amount of fault current. So the higher the fault current or the higher the overload, the faster the device will trip. And it represents this piece of the curve right here. And when you, so in your 51 device, you have basically three settings you have to be concerned with. The curve, which is this piece here, how it's sloped. There's a couple different definitions of different kinds of slopes that you can choose from. The tap, and the tap changes the curve from left to right. Increasing goes to the right. So if you have a tap of 1, it may be somewhere around here. Tap 2, somewhere around here, and so forth as it increases. And then finally, your time dial, which is your time delay and how far this curve is going to move up. So increasing the time dial moves the curve up. Increasing the tap moves it to the right. And generally, you set, say, for example, that you wanted a protection for 200 amps worth of cable. You would set your tap pickup on this 51 device to pick up at 200 amps. So basically this level here, somewhere around here at almost infinite time, would be about 200 amps. But then you see as the time gets smaller and smaller, that 200 becomes like 2 per unit, 400, 600, whatnot. So that's the function of the 51 device. It's basically used for overloads and short circuits within high impedance, like not bolted faults, high impedance short circuits. That's what it's intended to protect. I put in some information here about the difference between an electromechanical and numerical, but the take home is that the electromechanical had very limited number of taps and time dial adjustments, but the time dial was relatively imprecise. The numericals have almost a continuous step value. Like for example, tap here, you can set it from 0.25 to 25 in 0.05 steps. So you have a lot more resolution with the numerical relay than you ever did with the electromechanical. The next big component is the instantaneous trip, which is an ANSI device 50. The instantaneous overcurrent in its original form was just a solenoid, and it picked up at a specific current value that you set, and that was it. No intentional time delay. And that this curve kind of represents that. This part of the line is the minimum time it would take to operate. But essentially, what this is showing is that anytime you have more than 5 per unit current, as the way this is set, the instantaneous element is going to trip. So if you had a 1,000 amp breaker and you had a say a 6,000 amp fault on it, and with this relay setting, the breaker would trip almost instantaneously. It takes probably a half of electrical cycle for the relay to pick up, and then a few more cycles for the breaker to pick up and clear. But the point is that there's no intentional delay. So the only thing you really have to be concerned with in terms of setting is that pickup value. and increasing that pickup value increases the current at which the relay is going to operate. So it increases, goes to the right. Again, same issue with the resolution, much better resolution on the numerical relay versus what you had with the mechanical. And then just to add a little bit more interest to it, there's in the numerical relay world predominantly, they added something called a delayed instantaneous, which is sort of a counterintuitive, but it's very handy when you're coordinating relays with especially low voltage devices, because it ends up giving you a second level. So it gives you the response of a instantaneous, which is definite time, which means that if you get, like, for example here, if you're at 10 per unit current, breaker would trip right here at 0.4 or 0.5. So you have two settings. You have your delay, and then you have your pickup, versus the 50 without the time delay, just had the pickup. So you can combine them. So you can have, as a composite, you have your 51 time over current plus your 50 time delay, and then your instantaneous, so that, which is 50. So this would be for your bolted faults. Time delay would be for high impedance faults, or where you want the breaker to hold in to allow for coordination, and then your time delayed overload / high impedance stuff. So that's sort of an innovation that came out with the advanced and numerical relays. Here's an explanation of the different curve types for the 51 device, the time over current. This terminology comes out of the old electromechanical world, and basically it boils down to 4 that are going to be commonly used, and they're all based on inverseness of the curve. So you have your extremely inverse, which is this red line here. That's a very good curve to use if you have to coordinate with a fuse, or a low voltage circuit breaker, transformers to some extent. So it's a pretty often used, this extremely inverse curve. So that might be a good one to start with in a lot of applications. And then as it becomes less inverse, you go very inverse, moderately, the curves start to look like this. Here's a very inverse, and then an inverse. So they begin to look more like a definite time response versus a time delayed response. So the less inverse the curve is, the more it's going to kind of look like a no go or no go point. So usually in practice, you're in the very inverse or extremely inverse region for most. That's the curve type you use for most applications. There's a couple others. Definite time, that's the 50 response. That's the instantaneous, and that's just pick up in time. Pick up and then it trips. With a definite time, you can usually set a delay too. And then another one you might see is a long time delay, and long inverse. Long inverse would be used for motor overloads. So like a device 49 would be typical of a long inverse, and it would look a lot like the standard inverse, like this blue line, except it would be pushed up in time a little bit. So it allows for longer overloads, and it's good for and pretty much identical to motor overload curves. Here's kind of an important concept. The relay, that curve for the relay only represents when the relay picks up. It doesn't represent anything about how fast the circuit breaker can operate. So every time you apply a relay, you need to add an additional piece of time to compensate for how long it takes the breaker to operate. So the relay picks up, it tells the breaker to operate, and that breaker could be 3 cycles, it could be 5 cycles. Sometimes there's a delay in between that from interposing relay that takes additional time, and then there's all your accuracies. So this is the most important piece as a relay engineer that you have to be cognizant of, because it doesn't show up in the curve. This light blue stuff I actually drew in here based on math I did on a specific application. So your next device upstream, if you try to coordinate it, has to be clear of this light blue area. If it's not, then the two are going to be in a race condition, and you're not sure which would trip, so they're not coordinated. And here's a real quick rundown of what this encompasses. This area, it's the accuracy CT, and this is highly variable. Then it's a circuit breaker trip and clear time. Typically, that's for vacuum technology. It's 3 or 5 cycle breakers. So you'd add 3 or 5 electrical cycles to the time here. Interposing relay, you may have some relaying that adds a couple cycles between the relay and the breaker. That could be 1 to 3. And then for electromechanical, there was an over travel where the disc would actually spin and then have to have some inertia and would kind of overspin. So that was assumed as 6 cycles for that. So when you had your if you add them all, you have to add them all together. So you got your CT, let's say it's 6, plus your circuit breaker 5. Now you're at 9. I'm sorry, you're at 11. 5 plus 6, and then your interposing relay. Let's add another cycle onto that. So we're at 12 cycles. So this area here, you have to add 12 electrical cycles or 0.2 seconds onto that relay curve for your next device. This just shows you an example of that. Here is your feeder. Here's your main. Now you want the main and the feeder to be coordinated. So you set that main delayed past the feeder breaker by this amount of time, X, which is what you would have calculated in the slide prior, this piece right here. So this can range from the fastest you probably would ever do is 6 cycles, which is 0.1 seconds. It's very hard to get faster than that, practically. More realistically, you're at say 0.2 seconds or 12 cycles, or as much as up to 24 cycles with an electromechanical relay. And the takeaway is that the modern relays are much more precise, they're much faster, they're much more reliable, so you can bring this time down considerably if you're using numerical versus electromechanical relays. Here's just a real quick example showing this whole system put together with a relay combined with low voltage breakers. So you have a transformer in between. So you got your low voltage breaker, transformer, fuse protection. It's pretty typical, and then maybe an upstream relay. So this kind of shows a good coordination between your low voltage breaker, fuse, upstream distribution feeder relay, and this includes all the required time delays plus safety factor to allow everything to be fully coordinated. Lastly, just an example on what you need to do in EasyPower to utilize the relay. You select your relay, and then you also have to include a breaker. So the relay always has a breaker associated with it in EasyPower. And then this is an example of a multifunction numerical relay. So it's us as ABB REF, which is a feeder relay, model number 615, and it's ANSI because we sell ANSI versus IEC type relays, which is the European version. So they're a little different. Same hardware, but a different firmware. So this is the relay manufacturer. This is the relay type, multifunction, and the multifunction lets you put in the different curve pieces. Like for one, you have a 5051P, that's the phase, and then you'd let's see, that's all pretty much default values. This here for the one line, you put in like this is going to be a 50 instantaneous plus time overcurrent. So you type 5051, and that's what will show up on the one line in EasyPower. And this has 3 elements to it. It's got a phase, overcurrent 5051, neutral overcurrent 5051, and then a ground instantaneous only. Time delay only 51 device. So instantaneous time delay phase, instantaneous time delay neutral, time delay on the ground. So you have 3 protection functions modeled with this one device. And then when you go to the settings tab, this is the meat of it, where you put in the actual settings of each device. So you first select the function. So this one, 5051P, this pull down box would show the rest of them. So this is for the phase protection. You have your this is your tap. This one's set up for 0 to 5 amps maximum, and that'll vary. And then your time delay setting plus the curve. So curve, time delay setting, and tap. So this all covers your time overcurrent settings. And then for your instantaneous, you have the instantaneous tap, and you have a delay if you want it. So this 50 represents the time delayed 50, and then this one here represents just the instantaneous standard time delay. So we have for example, the instantaneous is set to 9x, 9 per unit, 3600 amps. We set the time delayed version to 1.8 per unit, 720. So this relay will trip at a delay of half a second at 720 amps. And then past that in time for lower currents, you have your curve, which this time dial and the tap, there is a correlation between the physical time on that curve, but it's not obvious. So like a lot of times in a low voltage relay or low voltage protection, it's sort of an obvious relationship. It's not. So you kind of either have to look at the curve family or just sort of through adjusting it trial and error to show where this is going to end up being, because it's not an obvious relationship. So that's how you would set it in EasyPower. And I try to keep it to 30 minutes so that we can do our digital switchgear presentation. So that's all I had for that pretty much completes the my section of the presentation.
Good job. And Nikita, let me give you the screen.
Okay, thank you, Jim. Thank you, Andrew. I always learn so much from you.
Thanks, Nikita.
Okay, so in review, hi everyone, by the way, good morning, good afternoon, good evening, depending upon where you're joining from. I'm Nikita Mishra. I'm a field application engineer for ABB Distribution Products, and I'm located I'm catering to the Midwest region. Previously, I worked as a product specialist in the Reliant segment, and that was digital substation products. I started my career as an electrical engineer at ESS Metron in Denver, Colorado, where I used to design low voltage and medium voltage switchgear, switchboards, and relay panels. So just wanted to give you a quick introduction of myself before I started. And so this has been a series of two, things that has been moving forward from electromechanical relays over to digital relays. Just wanted to do a quick review before we move on to the next topic in discussion, which is introduction to digital switchgear. So we covered a medium voltage relay versus a low voltage circuit breaker and the operating principles and how they're important, the protection applications associated with both of them. Then we also saw ANSI device numbers that are associated with different protection functions, like 5051 is for overcurrent, 87 is for differential, and so on and so forth. We also saw what are the principal components in medium voltage power system protection, which is instrument transformers, relays, and circuit breakers. So instrument transformers feeding us the information of the current and voltage into the relay, and the relay taking the action on the circuit breaker. So now, thank you, Andrew, for giving the relay coordination examples for electromechanical and digital relays, both. And as we saw the switch between electromechanical to digital, now let's move on to the next journey, which is digital switchgear. So these are the topics that I'm going to cover in today's presentation. It is going to be a very basic session in which I am going to be able to, give you an overview of the digital switchgear so that you can bring it up conversationally. And I'm not going to dive deep into the concept so that because the time is limited, and perhaps we can do another presentation where we dive deep into the codes and standards and the technical know-hows of it. So why digital switchgear is the first thing that we're going to cover. Then we are going to go over to what is a digital switchgear, the key components of switchgear, which is digital, like current and voltage sensors, protection and control relays, IEC 61850 communication protocol, and the benefits and challenges in incorporating a digital switchgear. So why digital switchgear? I mean, why is this term coming up so often nowadays in conversation? Why is it important? So let's go back to what our customers really want. So they want something that is simple. They want something that is smart. They want something that is flexible and reliable. So that is because every year, as time goes by, the complexity in the distributed networks is increasing because they're adding more sources. We're adding two-way communication. We're adding so many things because the demand is increasing and the technology is also flourishing. So as and when time goes on, I think you need to kind of adapt to the changing environment and be able to still be reliable and maintain the continuity of a network. So it should be on time. And moreover, we are seeing more environmental friendly requirements of late. And that is great for the future generations because it's more sustainable. It should be future proof, which means that if you want to expand it in the future, you should be able to. Of course, if you're installing a switchgear today, you want it to run for the next 20, 30 years. And then if you want to modify something, it should be possible. It should be a possibility. So sharing that and then being efficient, being easy. So these are the things that our customers want. These are the driving factors of why a digital switchgear would be a good move right now. So what is a digital switchgear? So by definition, shared with us by our colleagues at ABB, switchgear, I'm just going to take a moment and read out this definition. So switchgear with device information, device status information, current and voltage measurements, and commands are reliably transferred on a common communication bus. The common communication bus being the IEC 61850 communication protocol. It's an interoperability protocol between different vendors. So obviously in a substation or in a grid, not all the devices that are running are going to be from the same vendor. But now to maintain, to expert reliability, we want them to talk to each other and share their status. So that is something that can be enabled by a digital switchgear. Alternatively, or as a part of this, the the switchgear and its equipment condition monitoring and diagnostic information is also digitally available for advanced analysis. So what that means is like if we monitor our conditions like temperature, humidity, partial discharge, or circuit breaker status. So that should be available for further analysis at a later stage. So that is also enabled by a digital switchgear. So this is something that we have sensors and equipment in there, which is enabling us to do all of this stuff. Okay, my system. Okay. So it is the next phase in evolution of a switchgear. So what we want is more reliability, personal safety, simplicity, and also we want flexibility of design, right? So now IEC 61850 is the protocol standard that is used in a digital switchgear. If you want to maximize the benefits that you get from a digital switchgear, you have to use the IEC 61850 protocol. And it can work with having voltage sensors and current sensors and protection relays which have low energy analog inputs in them so that they can read the measurements from the current and voltage sensors. And it will be a preferred requirement. The preferred requirement would be that it's UL certified. Now there are different levels of digitalization that we see. You don't have to adapt to it and become the top level digital switchgear at one go, because everybody is different in owning the newness of things, right? So you can start slow, you can start simply with a base level 0, where you simply replace your instrument transformers in your current switchgear with your sensors. So the sensors that we use are like Rogowski coils for current sensors and resistive voltage divider for voltage sensors. You can also include conditioning monitoring sensors, so for temperature, humidity, and circuit breaker status. So by just doing this, what you're reducing is you're reducing cost, you're reducing footprint, you're reducing space, of course, because you're reducing the footprint, you're reducing the weight, because these current sensors are so much more lighter than the instrument transformers that you conventionally use. And then you eliminate the hazard of open CT and also CT saturation. and it's more safe for the personnel, the maintenance personnel and also operation personnel. The equipment condition is also monitored. So this is like a base level depending upon how comfortable the design engineer is with implementing or introducing digitalization into their own switchgear. So this would be like the base level. Now, we could take it a level up if we are comfortable with this and introduce IEC 61850-8-1, which includes MMS, which is Manufacturer Messaging Specification. So what that does is, if suppose you want a remote control or you want, SCADA, if you want to enable SCADA in your system. So what you're going to do is you're going to have a relay which is equipped with IEC 61850-8-1, and it's going to talk with the SCADA system. And also the IEC 61850-8-1 also has ghost messaging. So ghost messaging is basically generic object-oriented substation event, and the operation time is less than 10 milliseconds for distribution systems as per the standards required. And there's Ethernet cabling between the protective relays. So over here, what you're doing is you're reducing the cabling between the CTs and VTs and the relays, which is robust, in a conventional network. Over here, it's going to be one Ethernet cable coming from the current sensors and one Ethernet cable coming from the voltage sensors and going into the protective relays. And we save money on copper. We can customize it later depending upon the application. Now, the most amazing level 2 is where you include process bus communication, which is 61859-9-2 LE. This includes sample measure values. So what it does is it takes the analog inputs from current sensors and voltage sensors, and it sends it to a merging unit or protection and control relay, which has IEC 61859-2 LE, and it reads it and digitizes it to send it to the other and share it with the other relays, which have the same protocol in them. And in this level, you can also use synchronization devices and Ethernet switches. You can also use PTP or UL 1588 devices and fiber optic connection from base switchgear to substation. So this is improving flexibility and giving you so much more for your application. And you just need to change things on the IED because the relays are already sharing all the information that there is because of the sample measure value. So the real question is digital switchgear constructed any differently from the normal one? And can you make it out when you're looking at a switchgear in front of you? So as you can see in the picture that I've shown you on my screen, you cannot make out a difference from the front of the switchgear. Where you can make out a difference is at the back. Now, suppose you have two breakers where you have two 1200 amp breakers and you have a voltage transformer. That means that you have two sections right now. So you'll have a VT compartment because voltage transformer takes up that much space for the draw out compartment. And then you'll have a breaker compartment, and then you'll have another section which will be your breaker again. But now, as you can see over here, if you can see the arrow on my screen, the voltage sensors go into the cable compartment at the back and can also be used as a bus support. So you see how small they are? So right now you're reducing one full section because the breaker can go here and the breaker can go here. So you're reducing the whole footprint by one section. Now, the current sensors would go in the same place as the current transformers, as you can see over here on the breaker bushings. So you have the Rogowski coils here, which are connected with an Ethernet cable, and which is Cat5e or Cat6. And this is going to be the voltage sensor at the back in the cable compartment. Depending upon the vendor, they can also be used as bus support if they have enough insulation. So let's kind of dive deep into a little bit of, the key components of a digital switchgear that are used. So let's starting with sensors because they are level 0 requirements for a digital switchgear. So as we know, we know that Rogowski coils are old. Resistive voltage dividers, capacitive voltage dividers, all of these technologies are old. They've been there for decades. But what makes it so special is that, you throw the right things in the mix together and they make a very valuable product. So now you throw in Rogowski coils and you throw in your resistive voltage divider along with your IEC 61850 enabled device, and that will be a great product right in front of you, maximizing all the benefits. So that is how it is. These technologies have been there for long and everybody knows about it, but then throwing it into the correct application is what makes it so different. So it is using solid state components, and there's no or little ferromagnetic material in the circuit. So because there is no magnetic core, Rogowski coils have air core, and they basically have no CT saturation issues. And also we kind of eliminate the open CT hazard. And there's increased safety, reduced footprint, are much lighter and much smaller than conventional CTs and VTs. They have more flexibility when it comes to the range of voltage and current that they can actually read. And so for 7,000 volts or for 14,400 volts, you're going to use the same voltage sensor. And likewise for 1,200 amp or a 4,000 amp current sensor. You don't need to replace it. So going on to a little bit about Rogowski sensors, we know that they work on the principle of mutual inductance, and the output is actually a voltage, which is proportional to the derivative of the primary current. And what that means is that your device should have an integrator in that, so that they can integrate the secondary, integrate the output into the secondary current. And there is no magnetic core, so there is no saturation involved. There is no open CT hazard, and this makes it much easier for usage. So we also have fiber optic current sensors, which are used mainly in the high voltage applications because they're more costly. Voltage sensors are working on the principle of resistive voltage divider. There is no ferro resonance as it's non-inductive. Capacitive voltage dividers are used for high voltage applications, again, similar principle. And so the accuracy of these current sensors and voltage sensors would be 0.5 for metering, 0.5% for metering, and 5% for protection for the current sensors, and 0.5% for metering, and 3% for protection for the voltage sensors. Now, they have a very linear characteristic. I could delve deep into it maybe in another session when we look at the curves. Let's go on to the current and voltage sensor connections to the IED. As you can see, how we reduce cabling in a convention from a conventional switchgear into a digital switchgear is like you have your sensors, and then they have a Cat6 or Cat5e cable, which is industrial grade, which goes to the industrial grade adapter, and then that actually goes to your digital test plug if you need it to be going to a testing device. Or it can go directly to your protection relay, which should be equipped with low energy analog inputs. And we're saving so much on copper, right? Like as you can see over here, this is a colored picture of the same thing. And point-to-point wiring is eliminated, and we will see a picture of how we have eliminated the cable tray requirement in the whole switchgear layout. So the second key component for digital switchgear is IEC61850 communication protocol. Now, basically, IEC61850 communication protocol also has a few things involved with it. So the minimum requirements are that it is the device should be IEC61850 compatible. It should have vertical communication, which we just saw was MMS, which basically makes the relay talk to the SCADA system. Then you have the horizontal goose communication, which is a peer-to-peer functionality. It is on the horizontal bus, and it will be less than 10 millisecond operation time. And process bus is basically sample measure values, which is current and voltage analog signals, which are being shared by the devices. And you need IEC61850-9-2 LE sample measure values for actual maximizing your benefits. And you need low energy analog inputs. So preferred requirements would be IEC 61850 edition 2, which is the latest one, and UL certification. So why are we using IEC 61850 and not any other communication protocol like Modbus or TCP/IP or DNP3? Because IEC 61850 is an open and global standard for power system application. It actually defines all the objects that are there in your single line diagram. And it also enables interoperability between two different vendors or multiple different vendors, and because they all work on the same substation configuration language, and it's all going to be based on the data modeling that is done similarly with every vendor program. And it has three different things that you can achieve with it. You have goose communication, you have MMS, and you also have sampled measure values. So over here, we replaced copper with Ethernet, and as you can see, this was how it was before, and this is a lot of wires, right? And over here, it is so much more cleaner, and you reduce the footprint, you reduce copper, you're actually reducing the total ownership cost of the system. So that was kind of a rundown or quick basic concept of digital switchgear. Let me go into the benefits of having a medium voltage digital switchgear, the 5 S's, which are most important: safety, saving, speed, simplicity, and sustainability. So of course, safety comes first. So we have to determine that yes, this particular application kind of eliminates the hazard of having open CT secondary, and we have no CT saturation, so that is great. And then the solution is continuously self-supervising with maximized error detection. Then we are saving so much. We are saving on space, we are saving on footprint, we are saving on inventory costs, and we have energy savings because these are low power. We are saving on total cost of ownership. Speed, it has to be like great speed, and that is determined. Simplicity, it's fewer wires to install, fewer maintenance requirements on this whole process, so it's increased reliability. Sustainability, universal standards, IEC 67850 enables future system expansion, future load chains without any mechanical reconfiguration, because these sensors and voltages can actually cater to a lot of range, a huge range, so lower lifetime environmental impact. The benefits versus challenges of a digital medium voltage switchgear would be that we just saw the benefits. It's increasing your safety, it's in energy efficient and climate friendly, it's increased flexibility, reduced footprint, optimized weight, faster lead times, of course, because it's not very common out there, and faster installation and commissioning, lesser maintenance, and increased system reliability. Now let's look at the challenges, because nothing comes without challenges. So right now, if you want to digitalize your current existing switchgear, you must make sure that the devices you have in there are IEC 61850 compliant. If not, then you are not going to you're not going to reap the best benefits out of the whole digitalization process, right? And they should also have low energy analog inputs available within the device to be able to take information from current and voltage sensors, because those are specialized inputs that you need with your device. Now, in practice, we see that the relays are usually powered by the transformers, the instrument transformers that we use themselves. But if we are talking about a switchgear and not something like a revenue meter, which is outside of a building, then I think this should not be such big of an issue, because there will be a control power source within the switchgear for the relays to power up. But if not, if it is actually a revenue grade meter which is going to be put outside, so you cannot really power that up, and you cannot use this particular technology for revenue grade metering, at least as of now. And of course, it's application specific, so be sure to reach out to the vendor that you seek and explain them the application that you want to achieve, because the sensors are not out there to replace the current and voltage transformers completely. If you say that yes, they will be more popular in the future, yes, they will be, but they are not going to completely replace the instrument transformers that are currently there. So based on the application, a person who is a technical resource for such applications will be able to tell you exactly what to do with your particular design. So that would be the best and the most valuable thing that you can do. So thank you for your time and listening to me on the introduction to digital switchgear. This is very basic, and I hope that you can benefit from this session.
Wow.
And
that was a good job. We have several questions, and some came in on Andrew's part of the presentation. And they're under the chat box if you want to kind of preview them. Andrew, one of the questions that came up, I was curious, when you showed the coordination between a fuse, a relay, and a breaker, and you showed transformer protection, the question is, how do you know, or what portion of the transformer damage curves do you try to cover with each device?
That's a good question. And I typically, that damage curve represents the through fault current of the transformer. In other words, like you have a bolted fault essentially on the secondary of the transformer. And the curve is represents how much the winding of the transformer can withstand before it becomes thermally damaged. So it's only really good for practically about 100 seconds. Past 100 seconds, I don't even bother to coordinate with that anymore, because the transformers begin to differ. The reason is that that energy that is in the winding during that fault, during that first 100 seconds, that begins to transfer into the cooling medium of the transformer. So the response becomes different. It basically goes from a short circuit to an overload type condition. So the summary is I cut it off at 100 seconds, and I try to protect for at least the single and three-phase infrequent fault damage curve. Frequent fault damage curve is a little you could do it. It's kind of optional, but at minimum do the infrequent fault single and three-phase to 100 seconds. Past that, it's a whole different equation with transformers because they have a massive thermal mass to them. So you can't protect the transformer overload, from overload with just overcurrent. It doesn't work. You have to take into account the temperature of the cooling medium of the transformer, like for example a top oil temperature. So the short answer is 100 seconds.
Okay, good stuff. Nikita, on your presentation, can you see the chat questions I've sent you?
Yeah. Yes. Let me take a look. I'm just reading questions. So yes, I see a question where in level 0 of digitalization, why is the saturation eliminated? That is because the current sensors that we're using over here are Rogowski coils, and they have air core and not magnetic core, and that is why the saturation is eliminated. There is no CT saturation. Are there any inherent differences in response in relay breaker response times as a digital switchgear? I would say no, not really. It is going on a fast communication protocol that the relays are talking with each other, so it is very fast, and there won't be any such differences in response timing. It depends on what you have, the application, the protection application you have in place for the same. Then does this digital switchgear help with the supply chain disruption problem? Are they more available than the standard CT, PT, and relays, etc.? I would say that yes, like right now, it would be great to check with the vendor. Like if you come to ABB and, we can take this offline, if you can email me your question again. And we can take this offline, and I can actually provide you with an approximate lead time on probably the current and voltage sensors that we have in the market. But yes, because it's less used than the conventional CTs and PTs, so it would be wise to think that yes, it could be, but it's always good to double check.
Andrew, here's one for you. Regarding the curves and the separation between devices that you were referring to, is there an IEEE color book that has updated recommendations that you would refer to? Is that a fair question?
I'm sorry, I was on mute.
Oh.
The best IEEE publication out there probably is the Buff book, which is the 232, IEEE 232 standard. I think there's a newer version coming out with a different numbering. It's not IEEE 232 anymore, but I'm not familiar. However, the Buff book does go through a lot of detailed examples like transformer protection, motor protection. So it's a really good starting point. Beyond that, the mantra has always been the art and science of protective relaying. So it's always kind of a series of compromises. So past the Buff book, there's a lot of other publications available that the ABB has a bunch of them where you can discuss some particular, pros and cons of doing protection one way or the other and settings one way or the other. We have publications for that, and then you can always reach out to one of me or my team. We have our field application engineers are located throughout the country, you can contact Nikita or myself, and then we can either help you or put you in touch with someone that's local. That's what we're here for.
Here's another transformer-related question. How do you avoid a ground fault when you're first energizing the transformer?
That's an awesome question. It's not just a ground fault. You have inrush on the transformer, and the inrush characteristics of the transformer are totally different than its normal running. And that's the beauty of the digital relay, the numerical relay, is that you can set a startup curve, which will allow for a higher inrush level. And then after a predetermined set time that you set, like say I want this group of settings to be active when we first energize, but only lasts for 5 seconds. And then after 5 seconds, let's go into the normal setting, a different setting. So you can have 2 different settings that are automatically selected if you use a numerical relay, which will allow you to get much better protection of the transformer and eliminate any kind of inrush nuisance dripping.
Super. Nikita, so it seems like you need a UPS as a backup power supply for the sensors. Is that standard, or is there another way to get there?
Could you repeat the question? I don't see that.
No, I made it up.
Oh, okay. Yeah, I was like, okay. Yes. So what's the question again, Jim?
So is it the standard convention for powering the backup power for loss of power in the system? You use UPS or some other battery operated, or is there another way to do it?
So your digital switchgear would work exactly like your conventional switchgear. So if you have a backup, like suppose we have a control power throwover in the system, right? So usually when we have a throwover scheme for the control power, we usually have a UPS feeding the second source. So that could be implemented in a digital switchgear as well. So the whole control and protection system that we use in digital switchgear would be similar to the one that we have conventionally. The advantage over here is that we have a communication protocol which does all the talking between relays and sharing information. So you do not have to have a lot of cabling and wiring that needs to be done in that.
All right. And then is anyone else, or is there another communication protocol being developed aside from the IEC standard?
So right now, I do not think so, because they are developing and introducing more concepts on the IEC 61850 right now, and they're testing a lot of things like centralized protection, or the next big thing is going to be the virtualization of protection. So these are the things that are there in the pipeline in the industry right now for digital switchgear. So, at the moment, I do not know personally. I will love to double check and get back to you on that.
All right. We've overrun our time slot. Anything that we weren't able to get to, we'll follow up with a Q&A sheet. Thank you both for a very good presentation, and thanks to the audience for attending. Have a good day.
Thank you, everyone. Thank you, Jim. Thank you, Andrew.
Thanks.